In today's class, we'll focus on numerical solutions of first-order differential equations. Many differential equations do not have exact solutions. Therefore, in this section, we show one basic method and one more advanced method of solving such equations numerically. That method is called Euler's method. So Euler's method is named for the Swiss mathematician Leonhard Euler. Leonhard Euler made a huge number of contributions to mathematics, almost half after he was totally blind. When this portrait was made, he had already lost most of the sight in his right eye. It was Euler who originated the following notations: f of x, function notation; e, base of natural logarithm; pi, mathematical constant; I, imaginary number; sum or summation; and delta y or finite changed. There are many differential equations that cannot be solved. We can still find an approximate solution. To find an approximate solution to a differential equation of the form dy over dx is equal to the f of xy that passes through a known point x0 and y0. We write the equation as dy is equal to the f of xy times dx, and then approximate dy as the difference of two values y1 minus y0, and replace dx with delta x. This gives us y1 is equal to the y0 plus f of x0 y0 times delta x, and x1 is equal to the addition of two values x0 plus delta x. Therefore, we know another point x1 and y1 that is on the curve of the solution. We can now repeat this process using x1 and y1 as a known point to obtain a next point x2 and y2. Continuing this process, we can get a series of points that are approximately on the solution curve. The method is called Euler's method. We will practice with an easy one that can be solved. So let's take a look. One exercise: dy over dx is equal to the 2x. This is a differential equation. Initial value y0 is equal to the 1. So let's take a look at this example. So dy over dx is equal to the 2x. y0 is equal to the 1. So that is the y0 is equal to the 1. So dx is equal to the 0.5. So dx or delta x is the step size. So in the first step, our x0 is 0 and y0 is 1. So we can find x1 and y1. x1 is 0.5 and y1 is 1. So these values we can find using Euler's method. So next process, we can find x2 and y2. So when you substitute corresponding values x1 and y1 to find x2 and y2, we can get the values x2 is 1, y2 is 1.5. So next process, we can find next values x3 and y3. So as we can see here, x2 is 1, y2 is 1.5, x3 is 1.5, and y3 is 2.5. So when x is equal to the 2, y is equal to the 4. So as you can see, with our graph is increasing up, but is a approximately solution. So how to find exact solution? So given equation dy over dx is equal to the 2x, so given values x0 is 0 and y0 is 1. So dx or delta x step size is equal to 0.5. To find exact solution, first of all, we need to separate values. After that, we need to take integration on both sides. So from dy, antiderivative is y. From 2x, antiderivative is x squared, then plus c. C is the arbitrary constant. From x squared over 2, but 2 with the coefficient, with the denominator, we can simplify them. Then finally we can get x squared. So in the next step, we can substitute in place of x and the y the corresponding values 0 and the y. Y is 1, x is 0. Then we can find out c. So c is equal to the 1. So finally my equation will be y is equal to the x squared plus 1. So that is a quadratic function. Graph of the quadratic function is parabola. So it goes in this way. With blue color we can see exact solution or exact graph of the given function. So with red color we can see approximately solution or approximate graph. So this method is called Euler's method. Also, although numerical methods are generally used with equations that cannot be solved exactly, we choose these equations so that we could compare values obtained with known values. So we can compare with the graphs with blue exact, with red approximation solution. That's why we choose one of the easy exercises. dy over dx is equal to the 2x. So it's more accurate if a smaller value is used for dx. In this example, we know that our dx is equal to the 0.5. If it's will be the smaller value, less small than the 0.5, for example 0.1 or 0.2, it will be more accurate. It gets less accurate as you move away from the initial value. So in this case we get the 0.5. If it's more than 0.5, it's less accurate. It's less accurate for finding the graph of the given function. So applying this Euler's method, we can easily find the graph. Continuing this process, we find a set of points that would approximately satisfy the function is a solution of the differential equations. So we can find another exercises and solve using this Euler's method.